Good morning. My name is Shreya Patidar. In this video, we will cover internal first section C. Question number 1. Student faculty feedback data may suffer from issues like accuracy, completeness, and consistency. Discuss each issue in this context. Example: missing survey responses, contradictory ratings, purpose with other dimensions of data quality relevant to learning analytics. The answer of the following question is: the assessment of the data quality in student faculty feedback depends on the intended use of the data, such as evaluating teaching performance, improving course design, or supporting institutional decision making. The main issue include the accuracy, completeness, and the consistency, along with other dimensions like timeliness and believe, believability relevant to learning analytics. First, the accuracy. The accuracy refers to how correctly the data represents students' true opinions. In student faculty feedback, inaccurate data may occur when students give careless, biased, or random ratings or misunderstand the questions. Example: a student rate all the questions excellent without attending most classes. Here, if the feedback is used for general trend analysis, minor inaccuracies may not matter much. However, when used for faculty performance appraisal, accurate and genuine responses are essential. Now, second, completeness. Completeness measures whether all required feedback data is collected or not. Here, the example: some students skip the questions or do not submit the survey at all, leading to the missing responses. For example, we are filling the feedback form, and many of them had not attended the class, and still they are giving ratings according to their choice. Or some of them are not filling the feedback form. This may lead to the incompleteness. For general feedback summaries, a few missing entries may not affect overall insight, but for departmental analysis or teacher evaluation, missing data can bias result and reduce the representativeness. Now, third, the consistency. Consistency ensures that feedback data remains uniform and the logical coherent across the student course and the semester. Example: a student rated a teacher as excellent overall but poor in teaching method. A contradictory response, as you can see here, the similarly using different rating skills. Example: between 1 to 5 versus 1 to 10 across departments create inconsistency. For large scale comparison or analytics, consistent data format and interpretations are crucial. Other dimensions of the data quality in the learning analytics are timeliness. Timeliness: here, the feedback must be collected and analyzed promptly after the course ends so that the results are useful for immediate academic decisions. Reliability: here, feedback data should reflect the realistic and the reasonable opinions. Extreme or illogical ratings reduce trustworthiness. Third one, the value added. The collected feedback should contribute meaningfully to improve the teaching quality and student experience. Fourth, the interpretability. Feedback result must be easy to understand by faculty and administrators. Overly complex data presentation can limit its usefulness. Last one, the accessibility. Data should be easily accessible to authorized user, example, to the faculty management without excessive efforts or cost. Next question, handling missing student feedback values. Discuss approaches used as such as ignoring tuples, filling manual filling with constant mean, mode, and median, imputation classes, class specific imputation, or most probable value methods. To handle the missing student feedback value, we will sometimes we will ignore the tuple, we will fill it manually, We will fill it with the help of constant, or we can fill it with the help of mean, mode, median. So first we will see the ignoring the tuple method. First, handling missing student feedback values in student faculty feedback data. Missing values often occurs when some students skip questions, do not submit the survey, or leave certain fields blank. Handling these missing values properly is crucial to maintain the accuracy and the reliability of learning analytics. Different approaches can be used depending on the purpose of analysis and the amount of missing data. So the first one is the ignoring the tuple. If we have large amount of data, for example, we have thousands of tuple, in them we miss one or two tuples, then it does not affect much to the data. Let's see here. This approach involves removing records feedback entries that contain missing values. For example, if a student leaves several feedback questions unanswered, that entries record may be excluded from the analysis. This method is useful only when the number of missing values is small. Otherwise, it can lead to the significant data loss and the biased insights. Now, the second one, if for example, uh, if only 2 out of 500 students missed one or two responses, so those tuples can be removed without affecting the result. Now, second method, manually filling in the missing value. In the small data sets, missing feedback values can be filled manually based on the logical reasoning or faculty averages. Example, an administrator may fill an average rating for a missing response if the student has given consistent ratings in other questions. The limitation is that the manual filling is the time consuming and subjective, suitable only for very small data set. If we have large data set, then this is not possible to fill it manually. So this is suitable for a small database. Now the third one, filling with a constant value. Missing values can be replaced with a fixed constant such as 0 or the average or unknown. Example, if a student skip a question, the value not rated can be entered. Limitation, this can distort the average and reduce the data variability if overused. Fourth one, we can fill with the help of mean, median, or mode. Missing numeric feedback values can be replaced with the statistical measures. Mean. We will replace the missing value with the average of the existing response, useful for continuous ratings. Median here, median used when the data has outliers or skewed distribution. Mode used for categorical data such as course satisfaction level. For example, if most students rated 4 on one of 5 scale, then missing ratings can be filled with the 4. Now the fifth one, class specific imputation. Here missing values are filled using mean, median or mode specific to a class or a group. Example, if missing value belong to students of a specific department or a subject, use the average ratings from the same class or a course. Advantages are more accurate than global imputation since it respects group level differences. Now the next most probable value model based. In this advanced method, the missing value is estimated using predictive models such as regression, Bayesian inference, or decision tree induction. For instance, a model can predict a missing rating based on other ratings given by the same student. Example, if a student rated communication and the clarity high, the model predicts a high overall satisfaction score. This approach retains the data relationship and yield the realistic estimations. Now question number third. Here exercise is going to give the following data in the increasing order for the attribute age. Here the data is given in the increasing order. Now first we have to find using smoothing by beam means to smooth the above data using beam depth of 3. Illustrate your steps, comment on the effect of this technique for the given data. In the second part, we have to how might you determine the outliers in the data. In the third part, we have to find what other methods are there for data smoothing. So first of all, we have to create the bins. To create the bins, we first must see that our data is in the sorted form or not. So step one, sort the data, but here our data is already sorted. In step 2, we will make the partitions or equal bins, as we know that total number of data points are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. Here total 27 data points are here. So we will divide this 27 data points into the bins with the depth of 3. So 27 divided by 3, which is 9. So here we will create the 9 bins. As you can see here, we had created the 9 bins. Now in bin first we will place first 3, in bin second after these 3 we will place next 3, and similarly we will place all the data points into the 9 bins equally. Now in step 3 we have to calculate the arithmetic mean of each bin. To calculate the arithmetic mean, we will add all these three terms and divide by 3, so we will get the average mean of the each bin. Now let's see the arithmetic mean of bin 1 to bin 9. Now, now in step 4 we will replace each of the value in each bin by the arithmetic mean calculated for the bin. By adding, we will place all the mean of the bin from bin 1 to bin 9. So this method smooths a sorted data value by consulting to its neighborhood, and it performs the local smoothing. Now in B part, the outliers in the data may be detected by clustering, where similar values are organized into groups or clusters. Values that fall outside of the set of cluster may be considered as outliers. Alternatively, a combination of the computer and human inspection can be used where a predetermined data distribution is implemented to allow the computer to identify possible outliers. These possible outliers can then be verified by human inspection with much less effort than would be required to verify the entire initial data set. Now, in the C part, other methods that can be used for data smoothing includes the alternate forms of binding such as smoothing by bin's median or smoothing by the bin's boundary. Alternatively, equi-width bins can be used to implement any of the form of binding where the interval range of the values in each bin is constant. Methods other than binding include using regression techniques to smooth the data by fitting it to a function, such as through linear or multiple regression. Also, classification technique can be used to implement the concept hierarchies that can smooth the data by rolling up lower level concept to higher level concepts. Now, in the question number 4, in data integration for MCA MTech analytics, discuss schema integration handling the redundant data example, duplicate entries from multiple surveys and resolving conflicts in values. So answer of the question is in learning, analytics or institutional data systems, data integration involves combining data from multiple sources such as surveys, course evaluations or academic databases into a unified and the consistent view. This process helps administrators and analytics to derive the comprehensive insights from the feedback, and the performance data. The key challenges include the schema integration, redundant data, and the conflict value are the first, the schema integration. The definition schema integration is the process of merging the data structures schemas from different sources into a single coherent schema. In feedback context, different departments or semesters may use surveys with different formats or naming conventions such as faculty name in one dataset versus instructor in another, course ID versus subject code. So the solution is identifying the semantic mismatches, same meaning, different meaning. We use metadata and the mapping rules to align attributes. Create a global schema that standardizes the attribute means and format the cross dataset. For example, here you can see source 1, source 2 and the integrated schema. In source 1, we have faculty name. In source 2, we have instructor name. The integrated schema will show us the faculty name. In source 1, we have the course ID. In source 2, we have subject code. And finally, in integrated schema, we have course ID. The schema integration ensures that all data fields align properly for accurate analysis. Second, handling redundant data. Definition: redundant data refers to the duplicate or overlapping records appearing across multiple sources after integration. For example, in feedback context, a faculty member's ratings may appear multiple times. If same feedback survey was conducted by different departments or repeated by a student. For example, student ID 101 has multiple records. 101 faculty name Dr. Sharma and the ratings are 8. Again, 101 had given the feedback 101 Dr. Sharma and again the same rating. So here it is the example of redundant data. Techniques to handle this redundant data is the duplicate detection. Use method algorithms based on student ID, faculty name, and the course ID to identify the repeated entries. This student ID, faculty name, and the course ID will ID is unique for each student. This will help us to detect the duplicate data. Now the next one is record merging. Keep only one record of duplicate records or compute an average rating if values differ slightly. Now last, the data cleaning tools employ tools or SQL queries to remove the exact or near duplicate tuples. This step ensures data consistency and prevent overestimation or underestimation of the satisfaction scores. Now, the third, resolving conflicts in data value. The definition is conflicts occur when the same attribute has different values across source for the same entity. In feedback context, if one survey reports a teacher rating as 8 and another as 9 for the same course and same semester, a data value conflict arises here. Conflict resolution methods. To resolve this conflict, we have some method. First, the source priority. Trust the data from a more reliable or recent source, example, official university survey or the departmental survey. Next, the averaging or aggregation. We will compute the mean of conflicting values. For example, 8 and 9 is here conflicting values, so we will take the mean of them. So the average value is 8.5. Next, the rule-based resolution defines the rules. For example, prefer value from official databases if timestamp differs. The manual verification for critical cases verify directly with source, department or faculty. Proper conflict resolution ensure that integrated feedback data is both accurate and credible. Now, question number 5. We have to discuss the method mean max normalization, B z score, C z score normalization using mean absolute deviation, and D is decimal scaling. All these methods are used for the normalization. So first the min max normalization. can we define any value range and the linearly map the original data to this range. To calculate the min max normalization, our formula is x minus mean of x upon max of x minus mean of x. Now, second, the z-score normalization. The z-score normalization, the value for an attribute A based on the mean and the standard deviation. So, the value range of for z-score normalization is mean of A minus A upon standard deviation, comma, from mean to max the value range lies here. To calculate the z-score normalization, our formula is z is equals to x minus mu or mean upon standard deviation sigma. Now z-score normalization using the mean absolute deviation is a variation of z-score normalization by replacing the standard deviation with mean absolute deviation of A denoted by SA, which is, as you can see here, SA, which is 1 by n bracket V1 minus A bar plus V2 minus A bar and so on. So the value range is our from mean A minus A bar upon SA. Here AC is is the standard deviation with mean absolute deviation of A denoted by AC as it is here given. Now D, the normalization by decimal scaling, normalized by moving the decimal point of values of attribute A. The value range is from mean A upon 10 raised to power j to max A 10 raised to power j, where j is the smallest integer such that the max of vi upon 10 raised to power j which should be less than 1. Now next question we have to implement all this min max normalization, z-score normalization using mean absolute deviation and the normalization by decimal scaling. Now the first we have the normalization of the following faculty workload values are per semester is given here. Now to calculate the min-max normalization, our formula is x minus mean of x upon max of x minus mean x. So here in the given data, our data is already in the sorted form. So here our data minimum value is 200 and maximum value is 1000. So as we know that mean value and max value, so when we subtract max minus mean, we will get our range. So our range is 800. Now to compute this, as we know, these all data points are given in the question. To calculate the min max normalization, here our x is 200 and our minimum value is also 200. So 200 minus 200 upon range we had already calculated, that is 800. When we calculate it, our min max normalization is 0 for 200. Now for 300, our x is 300, our mean is 200 divided by our range. So we get our answer 0.125. Similarly, we will calculate the mean max normalization for the remaining three data points. So our result is 0, 0, 0, 0.125, 0.25, 0.50 and 1. Now to calculate the z-score normalization, our formula is z is equals to x minus mu upon sigma. Now, first of all, here we have to calculate the mean. To calculate the mean, as we know that the summation of all the terms upon number of terms. So, summation of all the terms upon number of terms is 5. When we calculate the mean, so our mean value is 500. Now, sigma, we have to calculate the standard deviation. The formula to calculate the standard deviation is x minus x bar whole square. Summation of x minus x bar whole square into under root upon n. Inside under root, everything will be inside the under root. So, as here you can see x minus x bar is 500 whole square plus for 300, for 400 and 600 and 4000, so on we will calculate, and which is divided by 5. When we calculate this, So our standard deviation is 282.84. Now we will compute this value into our z-score formula. Now we will compute this value into our z-score formula. When we compute this value into our z-score formula, we get z-score for the following data points as here: minus 1.06, minus 0.71, minus 0.35, 0.35, and the 1.77. Now in C we have to find the z-score normalization using mean absolute deviation. Using mean absolute deviation we have to find here, as we had already calculated the mean. Now to calculate the mean absolute deviation, our formula is summation of modulus value of absolute modulus or the absolute value of x minus mu upon n. So our mean is 500, and we calculated the x minus mu with the help of our given data points. When we substitute these values and take the summation divided by n, which is our 5, so our mean absolute deviation is 214. Now we will compute this mean absolute deviation into our formula, that is x minus mu upon mean absolute deviation. When we substitute this value, so our result is minus 1.25 comma minus 0.83 comma minus 0.42 comma 0.42, and the last one is 2.08. Now the last, decimal scaling normalization. To perform the decimal scaling normalization, our formula is x upon 10 raised to power j, where j is the smallest integer such that our max should be less than 1. As we know from the given dataset, our mean is 200 and our max is 1000. So here max is 1000. So according to the 1000, what should we take our j value so that our max will be less than or equals to 1. So here we know that x is our 1000. When we keep j as a 3, so 10 raised to power 3, 1000 upon 1000, which cancel out, and equals to 1. So our max is 1. Yes. Now we will calculate for this following data points. 10 raised to power 3, already when we put x is equals to 200 upon 10 raised to power 3, so our value is 0.2. Similarly for 300, 400, and 600 and 1000. So our result, the decimal scaling is 0.2, 0.3, 0.4, 0.6, and 1. Now the next question, using the feedback rating dataset, normalize the value 35 using min-max normalization. The range is given between 0 to 1. Z-score normalization, where sigma is equals to 12.94. In third part, we have to find the decimal scaling, and the last, to discuss which method is most sorry, sorry, discuss which method is most appropriate and why. Now the feedback rating value is where x given 35 and sigma is also given. So range, we assume that as it is not given in the question, so let assume the mean value is 10 and the max value is 50. Now to calculate the min max normalization, we require the minimum and maximum value. So that's why we assume the 10 and 50. Here x known 35, mean value is 10, max minus mean, which is 40. When we substitute, so our min max normalization is 0.625. Now for calculating the z-score normalization, so we substitute this value, and the sigma value is already given to us, so which is 12.94. When we substitute this value, we get 0.39. To calculate the decimal scaling, our formula is x upon xj, where max is our 50. So what should we keep here so that we can get the value less than 1? So when we put j is equals to 2, which is 10 raised to power 2, which is 100. When we cancel out it, so our x value is 0.1. Yes, it is less than 1. Yes. So we will calculate our decimal scaling for the given data point, which is 35. For 35 upon 100, it is 0.35. Now, in the D part, all four normalization method mean, max, z-score using absolute mean deviation and the decimal scaling can be used to standardize data, but their suitability depends on the context and the nature of the data set. Min-max normalization. Min-max normalization is best suited for the data that has known range like feedback ratings that usually lies between 0 to 50 or 1 to 10. It rescales that the data to a fixed interval such as 0, 1, preserving the relationships among the original values. This makes it ideal for feedback ratings analysis where relative satisfaction levels are the important and easy to interpret. Now, the z-score normalization suitable when the data is normally distributed or when you need to compare the data from the different scales or the distribution. However, feedback data often does not follow a perfect normal distribution, making this less intuitive for interpretation. Now, the last second, the z-score normalization using mean absolute deviation. A variation of z-score that is less affected by extreme values or the outliers, making it useful if a few students give abnormally high or low feedback scores. The last one, the decimal scaling normalization. This method divides the data by power of 10 so that the all values fall within the range of -1 to 1. It is a simple mathematical adjustment, but it does not consider the distribution or the variability of the data. Therefore, while easy to compute, it may not provide meaningful insights into rating patterns. Question number 8. Suppose the student project evaluation scores are given. Now partition into bins using equivalent frequency partitioning and equal width partitioning clusters. As the data is given, first we will sort the data, but our data is already in the sorted form. Number of values are 12 to divide into bins. Here data points are 12, so in each bin there will be 3 or 4 four elements. So we divided in three bins. So each bin will contain the four data points. Equal frequency partitioning, here number of bins k is equals to 3. So each bin should contain n is equal n, which is 12, and k divided by 3. So 4. Each bin will contain the 4 element. Starting 4 in the first bin, middle 4 in the second bin, and the last 4 will be in the third bin. Now equal width partitioning. Here we will compute the range and the width. As we know, the minimum value is 5 and the maximum value is 215. Now when we subtract both max minus mean, we will get our range, that is 210. And the width for k is equals to 3 is 210 divided by 3, so our width is 70. Now to compute beans into edges, so first initially age 0, which is our starting 5. Now for edge 1, as we had calculated the width, so we will add this width into our initial edge, which is 5. So our edge for edge 1 is 75. We will add 75 to the width, which is 70. So our second edge is 145, and the last edge 145 plus 70, which is 215. So beans, now the new bins are first bin will between 5 and 75 will consist the values from the 5 and 75. The second bin will consist the values from 75 to 145. 145 is excluded here, and the last bin 145 is included and 215 too. So according to these given data points, we substitute these data points according to the bin 1, 2, 3 edges, as you can see here. Now in the last part we have to perform the clustering. Let's assume centroids from the sorted score. From sorted score, we assume that the low value into the one centroid. In second centroid, we assume the middle values. In the last one, the high values, the values above the 120. So our centroid 1 is 5, centroid 2 is 110, and the centroid 3 is 215. As the data points are given, now to calculate the distance, as we know that equilidivision distance formula, that is x2 minus x1 whole square inside the under root. With the help of this formula, we will calculate the cluster 1, cluster 2 and cluster 3. We are divided into 3 clusters. So how we will calculate a 5 minus 5, which is 5 minus 5, which is 0, 0 whole square, which is 0. So our C1 is 0. Now we calculate the C2, 110 minus 5, which is 105. When we will put these values into this formula and calculate this all the all the values for the cluster. Now from these calculated values, we will check the minimum value in C1, C2, C3. Which one is minimum? C1 is minimum, so we will place C1 into into the 5 into C1 cluster. Now in second, 500 and 205. The 5 is minimum value, so we will place 10 into cluster 1. Now 699 and 204. Our minimum value is 6, so we will place 11 into cluster 1. By doing this here, for example, here 67, 38 and 143. The minimum value is 38, so we will place 72 into the cluster 2. In similarly, 210, 105 and 0. So 0 is the minimum value, so we will place 215 into cluster 3. We have to perform this method until our old cluster and the new cluster becomes same. So our new clusters are C1, C2 and C3, which contain these data points. Now now we have to calculate the new centroids. To calculate the new centroid, we will take the mean of our cluster 1, 2 and 3. The mean of the cluster 1 by adding all these data points having total 8 data points, so divide by 8. So our new cluster centroids are 24.25. For cluster 2, our centroid is 82, and for centroid 3, which is 209.5. Now with the help of this new centroid, we will again calculate the distance. So again we substitute these data points into our this given formula and calculating. This is our old cluster which we had calculated here. Now in this, our minimum value is C1, so our 5 will place into the new cluster. By checking this all, we had created our new cluster. So when we meet our old cluster and the new cluster, we find the dissimilarity that our 55 is earlier into first cluster, but now it is in the second cluster. Still they both does not match, so we have to calculate again. Now we are again calculating the mean of C1, C2 and C3. Now with the help of these new centroids, we will again calculate the distance. So this will become our old cluster and the new cluster will come after calculation. As you can see here, with the help of that centroid points, we had calculated the distance, and this is our old cluster. And now here we will compare our the smallest value, which is which is 14.85. So we will place 5 into cluster 1. Similarly, we will place all the values according to their we will compare all the values and place them into the clusters. When we match our old cluster and the new cluster, still we find that 50 earlier in the first cluster, now it is in the second cluster. Still not equivalent, so we will again perform the clustering. So first of all, we will find the new centroids C1, C2, C3. After finding that new centroids, we will again calculate the distance with the help of this new centroids. So when we calculated our distance, here this will become our old cluster. So this is our old cluster. Now comparing here, which is minimum value, as 9.84 is minimum value, so we will place 5 into cluster 1. Similarly, by doing this, performing this all, and finally we get our new cluster. When we match our old cluster and the new cluster, so here we found that there is no difference. It means that our final clusters are C1, which consists of data point 5, 10, 11, 13, 15, and 35. And in C2 cluster, we have 50, 55, 72, and 92. And in C3 cluster, we have 204 and 215. Now, the last question: use the flow chart to summarize the attribute selection techniques for feedback analysis. First, a forward selection, second, backward elimination, and the C, hybrid method. First, forward selection. In forward selection, as you can see this flow chart, we start, we begin here with initialize the reduced attribute set to be an empty set. If it is empty set, then we forward to the select the best attribute in the initial set using the statistical measure. Then we forward to the does the selected attribute exceed the stopping threshold. If it is yes, then we will perform this task, and if it is no, then we will directly forward it to this. If it is yes, then we will add the selected attribute to reduce the attribute set, and then we will go to the are there more attributes in the initial step. If there are more attributes, then again we will perform the step, and if there is no attribute, then we will end our selection, forward selection. The second one is backward elimination. Our beginning, the initialize the reduced attribute set to be initial attribute set. Then we will forward to the select the worst attribute in the reduced set using the statistical measures. Then we go to does the selected attribute exceed the stopping threshold? So if it yes, then we will move here, and if it is no, then we will remove the selected attributes from the reduced attribute set. Then we will perform there are more attributes in the reduced set. If yes, if there are more attributes, then we will again go to the select the worst attribute in the reduced using the statistical measures. Again we will perform this method. If no, then our program get end here. The last one is the hybrid method. In hybrid method, we start our beginning initializing the reduced attribute set to be an empty set. After that, we move to the select the best and the worst attribute in initial state using the statistical measure. We will select the best and the worst attribute here. Then we forward does the best attribute exceed the stopping threshold? If it exceed, then we will move this side, or if it is not exceeding, then we will move downwards here. If it is yes, then we will select the attribute to reduce the attribute set and remove it from initial attribute set. After this, does the worst attribute exceed the stopping threshold? Again, we will check that our attribute exceed the stopping threshold. If it is yes, then we will perform add all the remaining attributes in the initial working state to reduce the attribute set. Then if it is no, then we will remove the selected attribute from the initial working set. Then we will see there are more attributes in initial step. If there are more initial attributes, then we will again start from here, and if there are no attributes, then our program ends.